Hello and welcome to this lecture 3 of module 3. What we did in the previous lecture was to consider a small example of two equations, two linear equations and two unknowns, and then three equations in three unknowns, and solve that using a Gauss elimination technique. What we did was try to first motivate the Gauss elimination technique by solving the equations naturally. From this point onwards we will talk about the Gauss elimination technique. I have written down the matrix A and the vector B that we considered in the previous lecture in this matrix form. I have also shown here this lower triangle part of this matrix. We are going to make this lower triangle 0 using the Gauss elimination process. So what we did was use row 1 in order to get zeros over here and over here. Next we use row 2 in order to get 0 over here. When we ended up doing when we did that, we ended up with an upper triangular matrix. That means the values above, at and above the diagonal may be non-zeros, whereas all the values below the diagonal are definitely going to be equal to 0. Okay, so that is what the Gauss elimination process is going to lead us to. The first step that we said was R2 plus minus 2 divided by 1 into R1 and R3 plus minus 3 by 1 multiplied by R1. Okay. What that led us to, the first row does not change, so we get 1, 1, 1 and 4. The second row we definitely know that this term is going to be 0, that is through the choice of our alpha to 1. Okay. So we do not need to do any computation over there, we will just get 0 at this particular location. This is going to be 1 minus 2 which is minus 1, this is going to be 3 minus 2 which is going to be 1, and this is going to be 7 minus 8 which is minus 1. Okay. This term again we know for a fact that this is going to be 0, we do not do this extra computation, we will just put 0 over here. This is going to be 4 minus 2 which is going to be equal to 2, this is this term, sorry, 4 minus 3, not 4 minus 2, sorry, 4 plus minus 3 multiplied by 1, so 4 minus 3 which is going to be equal to 1, this is minus 2 minus 3 which is going to be minus 5, and 9 minus 12 which is going to be equal to minus 3 over here. Okay. So this is what we get at the end of step 1, and in step 2 we will have R3 plus 1 minus of 1 divided by minus 1, okay, minus of this coefficient divided by this particular coefficient, that is what we will have in step 3, and as a result of step 3 we will get this matrix as 1 1 1 4, that remains unchanged, 0 minus 1 1 minus 1 remains unchanged, and this is the row that will change. This remains unchanged because this guy is 0, so we will not do anything to it. This we know for sure that this value is going to turn to 0, so we do not do this computation, just put that as 0. So the only computations that we will do is minus 5 plus 1 which is minus 4, and minus 3 minus 1 which is also equal to minus 4. Okay. So this is the Gauss elimination process. What I will do in each of the steps is all the elements which we have changed through the row operations, I will put them in different colors. Okay. So we have changed this with row operations, we have changed this with row operations, we have changed this with row operations, 1 minus 5 minus 3 we have changed with row operations, 1 minus 5 minus 3 we have changed with the row operations. This 0 and 0, although we have done the row operations, that row operation was really the computation of this coefficient, we have not done explicit addition over here. So I will use a third color, the red color, to represent this. Okay. Likewise, I will use the red color to, okay, sorry, in this particular operation these values are not changed, so I will keep using white over here. Okay, this will, I will use red color because we know for a fact that this guy is going to be 0 after the row operation, so we do not change it, and these have been affected by row operations, so I will put them as yellow colors. Okay. So a few things that we had noted in the previous lecture as well is that Gauss elimination for an n by n matrix it has n minus 1 steps. Okay. N minus 1 steps, in this case it is a 3 by 3 matrix, and in a 3 by 3 matrix we had 2 steps, 3 minus 1 equal to 2 steps. In ith step we do Rj plus alpha ji multiplied by Ri, with j equal to I plus 1 to n. Okay. So in step 1 we will change Ri plus 1, that is R2, Ri plus 2, that is R3, and so on up to Rn. In this case n is 3, so we are changing row 2 and row 3. In the second step we will change, in the second step I equal to 2, so j is going from 3 to 3, that means we will do only one row operation, and that is going to be R3 plus negative of A32 divided by A22 multiplied by R2. Okay. So that was the row operations, row operation that we did. So this resulted in the lower triangular matrix 1 1 1 4 0 minus 1 1 minus 1 0 0 minus 4 minus 4. Okay. So next what we do is the back substitution step. Okay. In back substitution what we will first do is we will use the last equation to get, so nth equation we will use to get an, n minus 1th equation and the value of an in order to get an minus 1, sorry, xn minus 1, we will use n minus 2th equation and the values of xn minus 1 and xn in order to get xn minus 2, so on and so forth. So we start with nth equation. Okay. So our xn, in this case x3, is going to be equal to just b3 divided by a33, which is just minus 4 divided by minus 4, which is equal to 1. Okay. So that is the first step in back substitution. The second step in back substitution is going to be to use the n minus 1th equation in order to get xn minus 1. So our x2 is going to be equal to b3 minus a23 multiplied by x3 divided by a22. Okay. Why? Because our equation was a22 x2 plus a23 x3 equal to b2, sorry, not b3. Okay. So we take a23 x3 on to the right hand side and divide by a22. Okay. And what we are going to get is minus 1 minus 1 multiplied by 1 divided by a22, which is minus 1. So that is minus 2 divided by minus 1, which is equal to 2. Okay. So we will get x2 equal to 2 in the second step, and in the first step we will get x1 equal to b1 minus a12 x2 minus a13 x3 divided by a11, which is going to be equal to, in this particular case, 4 minus 1 into 2 minus 1 into 1 divided by 1. which is 4 minus 2 minus 1, that is 4 minus 3 are equal to 1, and that is the value of x1. Okay. So that is the overall Gauss elimination with back substitution for a general n by n equations. So writing down the algorithm for back substitution, in the back substitution step we go we let the I go from n to n minus 1 and so on up to 1. So okay, for I going from n down to 1, okay, we are going to compute xi is, so the ith equation is going to be a I xi plus a I comma I plus 1 xi plus 1 and so on up to a I n xn equal to bn. Okay. So we take all of these to the right hand side, so we will get a I xi is going to be equal to bn minus a I plus 1 x I plus 1 plus so on up to a I n x n whole divided by a. Okay, so this is going to be this term, and in the shorthand notation and dividing by x by a I we will get bn minus summation a I j x j j equal to I plus 1 to n divided by a I. Okay. So this is the value of xi that we are going to get. So for I equal to n down to 1 we are going to compute xi equal to bi minus summation j equal to I plus 1 to n a I j x j divided by a I. Okay. So this is how we are going to compute the back substitution step. Where the summation itself we are going to compute this as for j equal to I plus 1 to n. Okay. Let us call this particular term as some term say sum I equal to 0, we will call this, and then we will write this as sum I equal to sum I plus a I j multiplied by x j. Okay. And this is how we are going to calculate this particular sum over here. So we have bi minus this sum I divided by aii, that is going to be our algorithm, again a rough algorithm for the back substitution step that we are going to follow. In the next lecture I will take up an Excel example using Microsoft Excel to exactly show how we are going to do the Gauss elimination step and the back substitution steps. Okay. So this is overall what I have here for the Gauss elimination and the back substitution. Okay. Next what I am going to do is talk about two other methods which are the Gauss-Jordan method, and the next method is going to be the LU decomposition method. I will just use this particular example to show what Gauss-Jordan method is going to be and how it is different from the Gauss elimination method, and I will also use this same example to show the LU decomposition method. Once I am done with that, I will go and do one important thing, and that is to figure out how much computational effort the Gauss elimination method requires, and where the LU decomposition method and where the Gauss-Jordan method are going to find practical applications. Okay. So now we go on to the Gauss-Jordan method. Okay. What we did in Gauss elimination is we used the ith row in order to get the coefficients in the ith column 0 only for the rows below the ith row. Okay. So what we ended up with at the end of the Gauss elimination process, we ended up with a upper triangular matrix. So for example, when we started with the original, or when we started with this particular original matrix 1 1 1 2 1 3 3 4 minus 2, after at the end of the Gauss elimination step we ended up with the matrix 1 1 1 0 minus 1 minus 1 0 0 minus 4, which basically meant that we converted essentially these guys into zeros, okay, and only using so ith row in order to change the values of row I plus 1, I plus 2 and so on up to row n. Okay. We did not use ith row to do any changes in any of the upper rows. Okay. So that is what we actually did in the Gauss elimination process. In the Gauss-Jordan process, we are going to use the ith row in order to change all the upper rows as well as the lower rows, so that we will end up with an identity matrix. Okay. So the idea of the Gauss-Jordan method is okay. So the idea behind the Gauss-Jordan method is to convert the matrix A into an identity matrix using row operations, very similar to the Gauss elimination method. Okay. So step 1, so the thing that we did in step 1 in Gauss elimination method is we did R2 minus alpha 2 R2 plus alpha 2 1 multiplied by R1, R3 plus alpha 2 1 multiplied by R1. Instead, in Gauss-Jordan method, the first part of step 1 is divide row 1 with A11. Okay. So we divide the entire row with A11 so that the A11 element we will make that equal to 1. In this particular example that we had over here, this guy was already equal to 1. Okay. So we do not do any row operation, we do not do any first step over here explicitly, because we already have this equal to 1. If we did not have this equal to 1, we would have done the division. But when it comes to a computer, we do not know a priori that this particular number is going to be equal to 1. So rather than having an if statement to check whether this number is 1 or not, it is always more convenient to just go ahead and do this division step in a process that keeps repeating at each and every row. So in a computer implementation, we will indeed divide this particular row by A11, okay, then use row 1 to make zeros over here. Okay. So in case of Gauss elimination, I will write down this this overall matrix over here. Okay. At the end of the first step, the first part of the first step, we have divided R1 with A11, and when we do that, we will change all these guys, so to a different color. I have changed it to yellow color because we have done the row operation on that particular row also, okay. And then we will have R2 as R2 plus minus A21 multiplied by R1, okay. So previously we had this coefficient as the ratio A21 divided by A11. Now we do not need that ratio because A11 has become equal to 1 through the first operation, okay. So with now what we will do is this row minus twice this row is the computation that we will do. Now this number we know is going to become equal to 0. So in a computer implementation we are not going to do this particular calculation. So I will do put this in red color, and we will do rest of these calculations over here. So this is going to be 1 minus 2, that is going to make it equal to minus 1. This is going to be 3 minus 2, that will make it equal to 1. This is going to be 7 minus 8, that will make it minus 1, okay. This 3 is going to be automatically be converted to 0. So we will not do this particular step at all, we will just change that to 0. So this is what we will get over here. 4 minus 3 we will get this as equal to 1, minus 2 minus 3 we will get this as minus 5, again this is same as before, and 9 minus 12 we will get this equal to minus 3, okay. So the difference that we find between the Gauss elimination step and the Gauss Jordan step in the step 1 is what I will show. I will just box it with this purple color box. Rest everything is the same that we did in the Gauss elimination step. What is different in the first operation in the step 1 is that we have divided the row 1 with A11. So this is the result after step 1. Step 2 is going to be, one is divide R2 with A22, okay. So when we do that, now the first row of course has remained unchanged, 1 1 1 4, okay. 0 1, or I should actually be using yellow color. So 0 1 minus 1 1, because we have divided throughout by A22, okay. And then the second step, the second part of this step is going to be R1 should be equal to R1 plus negative of this coefficient multiplied by this guy. So negative 1 R2, and R3 should be R3 plus, again R3 was again 1 over here, so plus minus 1 multiplied by R2, okay. So this is, these are the steps that we will implement. So what that means is that we will have, once we have this particular guy, we will subtract from this particular equation, we will subtract this equation. So which means this term is going to become equal to 0, this is going to be equal to 2, and this is going to be equal to 3, okay. And likewise the row below has also been changed. This particular guy has not been affected, this 0 has not been affected, this particular element will become 0, we know for a fact that this will become 0, likewise we know for a fact that this will become 0, so we will not do the computation over here, okay. And then the computation will be done over here. This minus 5 is going to, as we had done before, this minus 5 again is going to be equal to minus 4, and then this minus 3 is also going to be equal to minus 4, okay. In general, for the Gauss elimination step, our Gauss elimination would have ended over here. The difference in Gauss elimination and Gauss Jordan now lie in both these rows, because we have divided throughout by this particular element, and then we have done the same thing over here. Okay. So, the Gauss elimination step, if we were to follow, it would have ended at this point, but in Gauss Jordan step we have the nth step also, and nth step. So, like Gauss elimination, we follow n minus 1 steps with a difference that we make the ith element equal to 1, but we have the nth step also, and in that nth step again we will have divide R3 with A33. So, when we do that, we will have 0 0 and we divide this by 4 minus 4. So, we will have 0 0 1 1, and then we will do R1 plus, in this case this guy is 2 over here. So, R1 plus minus 2 into R3, and then R2 and the coefficient over here is minus 1. So, it is just going to be R2 plus 1 into R1. So, sorry, R2 plus 1 into R3. It is actually not 1, it is minus of negative 1, and therefore it is 1. Okay. So, what change that will make? So, this 1 and 0 remain as they are, this 0 and 1 remain as they are. We know that these two elements are being made 0. So, we are not going to do explicit computations over here. So, we are putting this in a red color chalk, and the only things that are going to change are these two elements over here. Okay. We are essentially doing R1 minus 2 times R3. So, 3 minus 2, that is going to be equal to 1 is what we will have over here, and R2 plus 1 times R3. So, in the new R3 the value over here is 1. Okay. The old value of R2 was 1. So, 1 plus 1 is going to lead us to 2. Okay. So, this is what we get at the end of the Gauss Jordan method. The matrix A has been converted into an identity matrix, the matrix B has been converted into a solution matrix. So, what happens at the end? At the end of Gauss Jordan method, we have basically identity multiplied by x bar equal to b dash bar, where b dash is the b that has been transformed through the row operations that were performed on the matrix A as well, which basically means that what we get really on A in place of the vector b is the solution that we are seeking. So, no back substitution is required. Okay. So, unlike Gauss elimination step, we do not require any back substitution in the Gauss Jordan step, and the algorithm for Gauss Jordan is that we have step 1, step 2, step 3. So, that means we have n steps. Okay. And in the ith step we have Ri is nothing but Ri divided by Aii. Okay. So, R1 divided by A11, R2 divided by A22, or R3 divided by A33. Okay. So, for the ith step the first part of the ith step is R1 is this, and the second part of ith step consists of n minus 1 row operations. N minus 1 row operations is because row 1, row 2 up to row n except the ith row has been changed by ith row. Okay. So, the second part is going to be Rj is Rj plus minus a j I, because it is the ith column and the jth row, multiplied by R I, okay, where j is not equal to I. Okay. So, R1 is R1 plus negative of A1 2 multiplied by R2, R3 is R3 plus negative of A3 2 multiplied by R2. Okay. Likewise, in step 3 R1 is negative of A1 3 multiplied by R3, A1 3 multiplied by R3, R2 is negative of A2 3 multiplied by R3. Okay. And each of those row operation itself has multiple operations for each element in that particular row. And let us look at what we did in this in the third row operation. In the third row operation, the first element was 0, the second element was 0. As a result, we did not do any computation for the first and second element. The third element, we knew that these two guys are going to be equal to 0. So, we directly substituted those equal to 0 and only did the computation for rest of the steps. So, what this particular procedure or this particular step expands into, or sub steps expands into, is that for column j plus 1 for column I plus 1, I plus 2, I plus 3 and so on up to n, and then one more for the bth step. So, for k equal to I plus 1 to n plus 1, what we are going to do is ak, that means in a jk, because we are doing the jth row kth column A is going to be equal to that particular element jth row kth column A plus negative a j I, that remains as a j I, multiplied by the element, the kth element in the ith row, which is going to be a I k. Okay. So, this is what this particular step expands into. So, this is those yellow things that I have shown over here in this particular columns, and the red guys will also have that step, and that is going to be. So, the red guys over here in the third step are a1 3 equal to 0, a2 3 equal to 0, that means a j 3 equal to 0 for j going from 1 and 2. Okay. So, that is going to be a j 3, which is in the third step I equal to 3, in the second step I equal to 2, so on and so forth. So, a j I are going to be equal to 0. Okay. So, that is the step that we are going to implement. If we implement this step over here, there is going to be a problem that will be caused over here. As a result, this step will be implemented after this procedure is done. Okay. So, I will erase this from over here and I will put this at the end of it. Okay. And again, explicit computation of alpha j I is not needed, because alpha j I is nothing but a j I. Because what we could have done over here is alpha j I equal to a j I and then put a j I equal to 0. An easier way to do it is just replace this a j I from over here to over here. So, this is the overall procedural steps for the Gauss Jordan elimination. So, the algorithm is, in the ith step we will first divide the ith row with aii. Okay. So, aii is the diagonal element on the ith row. The diagonal element on the ith row is also known as the pivot element. Okay. So, we will divide the ith row by the diagonal element on we will divide the ith row by the diagonal element on the ith row, and then use ith row to make ith column zeros in row 1, row 2 up to row n except ith row. So, j given by j plus minus aj I rj, where j not equal to I, and this expands into these sets of equations. Okay. So, that is the algorithm overall for the Gauss Jordan method. The difference between Gauss Jordan and the Gauss elimination method is that in Gauss elimination method this step is not there. Okay. The second difference is that this particular coefficient is AJI divided by AII, and we have represented that as alpha ji, and it is not for j not equal to I, but it will be done for j equal to I plus 1, I plus 2 up to n. So, that is the difference between Gauss Jordan and the Gauss elimination method. Okay. So, what we have done so far is looked at Gauss Jordan, Gauss elimination methods. I will I will now next talk about another method which is known as the LU decomposition method, and in order to talk about LU decomposition method, I will use the results that we had in when we did the Gauss elimination method. So, this was our Gauss elimination result. From the Gauss elimination method we got this as the upper triangular matrix. So, let me write this upper triangular matrix as 1 1 1 0 minus 1 1 and 0 0 minus 4. Okay. Now what I will do is I will look at these coefficients. Okay, this was alpha 2 1, this was alpha 3 1, and this was alpha 3 2. Okay, and I will create a matrix which is going to be a lower triangular matrix, okay, containing this alphas in the lower triangular elements, which I will write this as negative of alpha 2 1, negative of alpha 3 1, negative of alpha 3 2. Okay. So, what we get over here when we do that is 0 0 0 0 0 0, okay, and alpha 2 1 was minus 2. So, negative of alpha 2 1 is plus 2, alpha 3 1 was minus 3. So, negative of alpha 3 1 is plus 3, and alpha 3 2 was 1. So, negative of 1 is what we write over here. Okay. So, this is one matrix, this is the other matrix. Let us take a product of these two matrices. Oh sorry, not 0 0 0, I should be putting 1 1 1 over here. Okay, my mistake. Okay. So, we have this 1 1 1, we have put zeros in all the upper triangular elements, and the lower triangular elements we have put that as negative of the coefficients that we have used in the Gauss elimination step. Let us see what product we get. This is going to be equal to 1 1 and 1. This will be 2 plus 0 plus 0, that is 2, that is 2 minus 1, that is 1, 2 plus 1 equal to 3, and this is 3, 3 plus 1 equal to 4, and 3 minus 1, that is 2 minus 4 equal to, so 2 minus 4 equal to minus 2. Okay. So, let us see what matrix this is. If we compare this with matrix A, 1 1 1 2 1 3 3 4 minus 2, that is exactly what we have got by multiplying these two matrices 1 1 1 2 1 3 3 4 minus 2. Okay. So, this is a lower triangular matrix L, this is an upper triangular matrix U, and this is the matrix A. So, LU decomposition is nothing but any matrix A can be expressed okay. The choice of the lower and upper triangular matrix is not unique. Okay. This is just one L and U matrices that, excuse me, this is just one L and U matrices that we can get through the Gauss elimination process. Okay. So, we start with A and perform the Gauss elimination. Okay. The Gauss elimination will give us the matrix U, which is the upper triangular matrix, and it will also give us coefficients of row operations. Okay. We take these coefficients of the row operations, negate them and put them in a lower triangular matrix, and we will get that lower triangular matrix L, and that lower triangular matrix L is just 1 1, or in general for an n dimensional case the diagonal elements are all 1, the upper triangular elements are 0, and the non diagonal elements are minus alpha 2 1 and so on up to minus alpha n 1, minus alpha n 2, and so on up to minus alpha n comma n minus 1. Okay. This is what our lower triangular matrix is going to be. I will rewrite this lower triangular matrix over here in a more general form. Okay. So, this is what we will get. Okay. 1 0 0 0 0 minus 2 minus alpha 2 1 1 0 0 0 minus alpha 3 1 minus alpha 3 2 1 0 0 0, and so on up to minus alpha n 1 minus alpha n 2 minus alpha n 3 up to minus alpha n n minus 1 and ending with the number 1. Okay. So, this is the lower triangular matrix. The upper triangular matrix is what we get as a result of the Gauss elimination step, and the product of the two matrices is going to be the matrix A. So, that is the idea behind the LU decomposition. Now, question is, where is LU decomposition useful? So, fine, we have now gotten the matrix L and we have now gotten the matrix U. What do we do with the matrix L and the matrix U? And the answer to that question is that we can use these LU matrices that we obtain in order to get this solution of Ax equal to b. Okay. So, if we have performed the LU decomposition and obtained the matrix L and the matrix U, we will be able to write this particular equation as LU x equal to b. Okay. Let us write u multiplied by x equal to some other variable, say y. Okay. If u x is going, we are going to write this equal to y, we can write Ly equal to b. Okay, where the matrix L has a form of this type. Okay. What we get in this particular form is that the diagonal elements are all 1, okay, and what we get is the upper diagonal elements are all 0. So, instead of a back substitution step, we use a forward substitution step to get L. Not to get L, sorry, to get Y. Okay. So, the forward substitution step, again this is the original B matrix, the unchanged B matrix. In the LU decomposition case, we apply the Gauss elimination only to the matrix A, not to the matrix composed of A and B together. Okay. So, we just apply the LU decomposition to matrix A, and then with a combination of forward and backward substitution we try to solve this particular problem, and the forward substitution is going to be y1 equal to b1, y2 equal to b1 minus a21 y1, and so on, yi equal to bi minus summation of a I j yj j equal to 1 to I minus 1, okay, and so on up to n. So, this is what we will do in the forward substitution step. When we perform the forward substitution step, we will get the matrix Y. Okay. So, Ly equal to B, we are solving in order to get matrix Y. So, result of the forward substitution step is y bar equal to y1 y2 up to yn. Okay. y1 y2 up to yn is nothing but the solution of the equation ux equal to y. Remember, we have substituted ux and replaced it with y. So, the second equation is going to be ux equal to y, where y is obtained from over here, and you can solve this using backward substitution. Okay. And when we solve this using the backward substitution step, we will indeed get x as a result of the backward substitution step. The backward substitution step is exactly the same as the backward substitution steps that we have considered, we have discussed when we talked about the Gauss elimination method. Okay. So, that is how we solve the equations using the LU decomposition method. So, to recap, what we have done so far is the following. Started with two equations in two unknowns, two linear equations in two unknowns, and saw the geometric interpretation, which we said was intersection of hypersurfaces. We took a small aside into the whole idea of vector spaces and tried to motivate a different geometric interpretation as a linear combination of various vectors. So, the two geometric interpretations we initially considered. After that, we started talking about the Gauss elimination method, and also we talked about backward substitution. we specifically took a 2 by 2 and then a 3 by 3 example to talk about the Gauss elimination method, but tried to expand it to a general n dimensional system in n unknowns. That is what we talked about, that is what we did when we talked about the Gauss elimination method. Then we took two other methods, which is the Gauss-Jordan method and then the LU decomposition method. Okay. So this is what we have done so far. Now the question is, why would you use Gauss-Jordan method, or why would you use Gauss elimination method, or is it actually useful to learn about an LU decomposition method when we already have Gauss-Jordan method as a way of solving. Okay. So to the answer to that question is that the Gauss elimination plus backward substitution method is really the workhorse. That's the method that is typically used in most example. This is the workhorse, or it is the most popular method. The reason why it's most popular method is because it compared to the other methods, it has the lowest amount of computational effort required. So when n is going to be of an order of 1 million, a small factor also becomes a very large number, because as we will see in the next lecture, these methods scale as n to the power 3, which basically means that the computational effort of a matrix of the size 10 to the power of a size 1 million, which is 10 to the power 6, the computational effort is of the order of 10 to the power 18 operations on that particular matrix. So it becomes really a big issue how much computational time you are going to spend in order to solve these problems. As a result, this Gauss elimination plus backward substitution is the workhorse. There are a couple of modifications that I am going to talk about in the next lecture that are very essential, which we have not yet covered. The Gauss-Jordan method is very popular also. A lot of people actually prefer to use Gauss-Jordan over Gauss elimination as well, but it is especially useful in finding inverse of a matrix. And finally, the LU decomposition method is useful when we have to solve repetitively the equations of the form Ax equal to Bm, where the B keeps changing with every iteration. So we will see examples of this type in module 8 and module 9 when we talk about basically the ODEs, ordinary differential equation boundary value problems, and partial differential equation problems, where those problems get converted into linear problems of this sort, where the matrix A does not change often, the matrix A remains constant, it is the matrix B that keeps changing. So by removing the Gauss elimination step and replacing it with forward and backward substitution step, we can get significant improvement in the computational accuracy. Please keep this in mind when we go to module 8 and module 9, where I will spend a few minutes, maybe 15 minutes to 20 minutes, talking about where we encounter problems of the nature Ax equal to Bm, and in what cases methods such as this modified LU decomposition method can be used. And to finish off this lecture, I will talk about the Jordan decomposition to find the inverse of matrix A. And what we do over that is we write the equation in the form A inverse equal to I. Okay, so what we have done is we have just replaced x bar with A inverse, and we have replaced B bar with I. Okay, so if we were to then get a matrix of the form AI and do row operations, okay, and then we were to do row operations on the matrix AI, and using the Gauss-Jordan method. At the end of these row operations, what we will be left with is the identity matrix onto this part, and what we get on the right hand part, the last n equations, is going to be A inverse, because what we are solving by doing this particular set of row operations is we are solving the equation A inverse equal to I. Okay. So by using a Gauss-Jordan decomposition on a matrix formed by concatenating A with an identity matrix of n by n dimensions, what we will end up getting is the A inverse at after Gauss-Jordan. Okay. This is nothing but saying I times A inverse equal to A inverse. Okay. That is what this particular thing represents, and the result that we get over here is the inverse of the matrix A, and that is the Gauss-Jordan method. And finally, just to leave you off with a small question, when we started off with this particular example, this matrix A had the form 1 1 1 2 1 3 3 4 minus 2, okay, which was equal to 4 7 9. So instead of this particular form of matrix A, what if the matrix A looked like 2 2 3, and we had to do Gauss elimination, because now when we do R2 minus 2 R1, we will get this as 0, this as 0 and 1. Our A22 has become 0. In that case, how do we proceed forward with the Gauss elimination? Okay. So I leave you off in this lecture, sign you off in this lecture with that particular question. In lecture 4, we will pick up with this question and then talk about a more appropriate way of doing Gauss elimination, and that is Gauss elimination with partial pivoting. Okay. So see you all in lecture 4. Thanks.